Welcome to Lecture 7 of Physics 506. In this lecture, we're going to be talking about rotations and how rotations are related to angular momentum. So in quantum mechanics, we define a vector operator via the following relation. A vector operator has three components. Those components depend upon what basis I'm working in, but if I work on the Cartesian basis, those components will be x, y, z. And we look at the commutator v sub I with L sub j, and that commutator, if that commutator equals I h bar epsilon ijk v sub k, where epsilon ijk is the completely antisymmetric tensor, and if you like, you can think of that repeated index as an implied summation using the Einstein notation. Very oddly, if we instead defined it as the commutator of Li with Vj, it is also equal to IH bar epsilon ijk Vk. You might have thought that there should be an extra minus sign, but you see when I make the difference and write it as Li Vj as opposed to Vi Lj, I've done two things. I've interchanged the order of the L with the V. That gives us a minus sign. But I've also interchanged I with J, because you can see it's now an Li as opposed to an Lj. And when I interchange I with J in the completely antisymmetric tensor, that changes the sign of the completely antisymmetric tensor. So I get a minus sign on both sides, which cancels. So it turns out that you can never get wrong the defining property of a vector operator. It's either Vi commutator with Lj or Li commutator with Vj. Both are equal to IH bar epsilon ijk Vk. All right, so we're going to be talking about rotations. I want to make sure you understand one of the pivotally important properties about rotations, in that two rotations do not commute. So the first thing to note is that rotations form a group. That means they're closed under multiplication, and there's a unique inverse. That means if I do any number of rotations, I can always represent the final thing in terms of a single rotation, getting from one point to another. In addition, if I do any rotation, I can always find the inverse rotation that gets me back to my starting point. But this group is a non-abelian group, because when we apply two rotations in one order, they're not necessarily the same as if we apply them in opposite orders. So in this case, imagine taking a book, and feel free to actually go and get a book and put it on the table when I talk you through this and go through the exercises yourself. If we were live, I would be doing this with you. Take the book and rotate it 90 degrees in a counterclockwise direction about the vertical axis, and then rotate it 90 degrees again in a counterclockwise direction about the horizontal axis. And you will end up with a final picture that is like what is shown there, with the book oriented in that fashion. If instead we first rotate it about the horizontal axis and then rotate it about the vertical axis, we find it will be in the configuration illustrated in the second piece. And you can clearly see those are two different orientations. So these two rotations do not commute with each other. You don't get the same result regardless of the order in which you apply the rotations. The order matters. And whenever the order matters, you have what's called a non-abelian group. And non-abelian groups are just harder to work with than abelian groups. But they're not something you should be afraid of simply because the two different operations don't commute with one another. Now, the claim with rotations is that all rotations can be written in the following form: a rotation with respect to some angle about some axis. En is a unit vector that corresponds to the axis, and alpha is the amount of degrees that we're rotating about that axis. And in the quantum mechanical situation, we're going to write that as exponential minus I alpha over h bar En dot L. That would be an operator that is a sum over components of L in an exponential. Okay? Now, if you look back at what we did with spin matrices in Lecture 1, we showed that rotations hold there if we were to replace the L by S equals h bar over 2 sigma, and the factor of 2 in that representation where we transform to the Pauli spin matrix notation is very important. All right, so let's assume that we make a transformation on states. Psi goes to R acting on psi. This is a unitary transformation on the states. You can easily see, because that exponential has an I times the Hermitian operator, exponentials of I times Hermitian operators are always unitary. Then if I look at what happens with O acting on psi, remember, O acting on psi, the operator just maps me to another vector. So the transformation of that new vector is just R acting on that vector. So it's RO psi. And now I just multiply by 1 in the form of R dagger times R. And I recognize that in the new frame where I'm working with R times vectors, the new operator is ROR dagger. So that tells me that after I do this rotation or transformation on the states, the operators transform as O goes to ROR dagger. Okay. Now, oftentimes when you're working on transformations of operators, it can be confusing as to whether or not it goes as the dagger of the transformation times the operator times the transformation matrix, or the opposite way, as it does with the rotations here. And in order to get that straight, you often have to go through a simple two-line derivation like what was given up here in order to figure out the right way in which it works. Okay? Now, on the homework, we showed that this Hadamard transformation, R LZ R dagger is equal to LZ, and R LZ R dagger was cosine alpha LX plus sine alpha LY, and R Ly R dagger is minus sine alpha Lx plus cosine alpha Ly. If you remember, this was done with a Hadamard identity that did not truncate, but it got into a repeating pattern, and we could then recognize that we had the power series for the cosines and the sines in the respective places, and we can actually just sum that series and get the full transformation of these operators. Now, since a vector operator satisfies the same commutation relations as angular momentum does, indeed you can think of the fact that angular momentum is a vector operator, because if I go back to take a look at the vector operator relationship, commutator of Li with Lj is IH bar epsilon ijk Lk. That's the commutation relation for angular momentum. So given that, this means that the transformation that we have done here actually works for all vector operators as well. In particular, what it says is e to the minus I alpha Lz over h bar Vi e to the I alpha Lz over h bar can be written, if I think in terms of the x, the y, and the z components, as a matrix cos alpha sine alpha 0 minus sine alpha cos alpha 0, 0, 0, 1, and written as matrix vector multiplication in the way that is shown for you on the screen. Okay? Now, if we simply permute the index in the exponent, z goes to x goes to y, and we think of permuting the relevant terms in the matrix in accordance with the way that the indices were permuted, we can find that the Hadamard transformation for an Lx and for an Ly rotation are given by the two matrices that are shown for you here. I would like you to pause the video and very carefully work this out if you're having any trouble with it. We are simply doing a relabeling of the axes, the x and the y and the z axes, and we're then doing that transformation onto the operator O of x. If you want to work out that transformation as a matrix multiplication, it'll have the form of a matrix on the left multiplying OZ multiplied by the transverse of the matrix on the right. And the matrix that corresponds to the interchange of the XYZ is just a matrix that has zeros and ones in such a way that you map x to z, y to x, and z to y. Okay? So you should be able to work that out for yourself. You also can just think of it in terms of just doing a relabeling and moving rows and columns around. In any case, you should be able to verify this result for yourself. All right, now what about the general case? In the general case, we have an exponential of an en dot L. And of course, en dot L is going to just be a summation of an Lx and Ly and an Lz with some numbers. If the axis is pointing in the theta phi direction, then en is given by sine theta cos phi, sine theta sine phi cos theta. And if you remember the unit vectors in spherical coordinates, I can also think of an e theta, which is cos theta sine phi minus sine theta. Then an e phi, which is minus sine phi cosine phi 0. The e phi points in the xy plane, and the e theta is perpendicular to the en and the e phi. So we can actually use the results that we already calculated to work out what the general result is, assuming that the same form holds if instead of using Cartesian instead of saying my I, j, and k were Cartesian coordinates, I say they're n theta phi. Okay, so what we need to show then is that the commutation relations for the vector operator, which I'm writing in the form of L beta v gamma, is I h bar epsilon beta gamma delta v delta, that holds when beta, gamma, and delta are chosen from n theta and phi as opposed to x, y, and z. Okay? Now, in order to do this, what we have to do is we have to recognize that there is a orthogonal matrix that transforms us from the XYZ coordinate system to the n theta phi, and I want to do it in such a way that this matrix takes the z direction to the n direction, the x direction to the theta direction, and the y direction to the phi direction. Now, from just the definitions of en, e theta, and e phi, we actually have the matrix. It's given by cosine theta, cosine phi, minus sine phi, sine theta, sine phi, cosine theta, sine phi, cosine phi, sine theta, sine phi, minus sine theta, 0, cosine theta. What you can see here is you can see if we take the vector en and write it as a column, what we've done is we've written this as a column en, e theta, e phi. I'm sorry, e theta, e phi, en is the way that we've written it. E theta, e phi, en as columns. That's what the O matrix is. And what we really need to know is that O transpose O is equal to 1. You can verify that for yourself if you don't recognize that that is an orthogonal matrix. So now let's see how do we make this transformation from the Cartesian system to our new system. Well, the V beta is equal to sum over J. I really should think of that as O beta J Vj. I wrote it as O ij Vj, but you really should be thinking of it as O beta J Vj. And then, so when we write these transformation matrices, you should think of the second component of the matrix as being Cartesian and the first component as being in the new basis, which is our spherical basis of n theta phi. And then what we have is we can write V beta L gamma as the summations of the OI prime, OJJ prime over the I prime variable. And because we know that the commutator of VI with LJ is epsilon, or VI prime with LJ prime is epsilon I prime, J prime, K prime, VK prime, we can then write V beta L gamma as IH bar O I prime, or if you prefer O beta I prime, O gamma J prime, or O J J prime, epsilon I prime, J prime, K prime, VK prime. Now, what we want to do is we want to write the VK prime in terms of the spherical coordinates, and you can see now I'm using the indices for the spherical coordinates here. We'll write that as OK prime transpose delta O delta L VL. You see, because O transpose O is equal to 1, that matrix multiplication where I sum over the delta index just gives me a delta K prime L. So that will equal VK after I've done all of that summations. Okay, so we can substitute that in for the VK prime. And what we're going to do then is we're going to use the O delta L VL to create V delta. And then I'm going to take the transpose of O transpose K prime L and write it as O delta K prime, where those delta indices are spherical in the spherical representation, just like the I and the J indices are in the spherical representation as well. So what this tells us is if, and now I'm going to be changing to a general argument, if the sum over I prime J prime K prime of epsilon I prime J prime K prime I prime J J prime K K prime is equal to epsilon I J K, if that holds, then we know that we can just use the same formulas we used that we worked out explicitly in the Cartesian form. We can use it in any basis that's related to the Cartesian basis by an orthogonal transformation. So in this case, we can be thinking about the IJKs in the spherical basis, but actually, since we're going to do this argument generally, this is something that actually holds for an arbitrary transformation. Okay? And what that would say is then in the new basis, we would have V beta L gamma is I H bar epsilon beta gamma delta V delta. Okay? So the way to check this is just to explicitly work it out. All right, let's look at the case where I equals J equals N. Okay, so if I equals J and they're both equal to N, what we find is we get epsilon I prime J prime K prime, O N I prime O N J prime O K K prime, and I'm summing over I prime and J prime. But the product O N I prime O N J prime, you see if I interchange I prime with J prime, that's symmetric. But if I interchange I prime with J prime and the epsilon I J prime K prime, that's antisymmetric. It changes sign. That means when I sum that over I prime and J prime, it's going to equal 0. And indeed, the commutator of Vn with Ln is equal to 0. Let's look at the case I equals N and J equals theta. Okay? Now I'm going to just enumerate all of the terms. I have epsilon xyz, O nx, O theta y, O delta z, epsilon yzx, O ny, O theta z, O delta x. And then you can go through and work out all of the extra terms. There's a total of 6 of them. I'm not going to read them out for you. If you like, you can pause the video and just work them out for yourself. It's essentially just bookkeeping to make sure you get all of the terms. Now, I've organized it in such a way that in the top row, all of the epsilons are 1 because those are the even permutations of x, y, z. And in the bottom row, they're all -1. Now, if you look carefully at what you get when you work that out, you find that that's actually equal to the determinant of the matrix, O. Remember, that O is a 3 by 3 matrix. Its determinant is a product of 3 elements summed with a plus or a minus sign. And indeed, carefully do this. And again, I really hope you pause the video and carefully work through this to verify that that expression is actually the determinant of O. Now, because O transpose O is equal to 1, the determinant of O transpose times the determinant of O is equal to 1. But the determinant of O transpose is equal to the determinant of O, so that tells me the determinant of O squared is equal to 1, or the determinant of O is equal to plus or minus 1. Now, for rotations, we find the determinant is always equal to +1. You can just calculate the determinant of the explicit orthogonal matrix that we showed above to verify that it's equal to +1. And that means that we'll get +1 in the case where I is equal to N and J is equal to theta. And that's exactly what we're supposed to get, +1. Okay? And then you can work it out for the other cases, but you can very easily verify that all the other cases fall into one of these two situations. They either have two indices the same, in which case you'll get 0, or they have indices that are different, in which case you'll get a determinant, which will end up being plus or minus 1, depending upon whether or not you have an extra transformation. Okay? So what this tells us is that after we've done the rotation, the algebra for angular momentum in the spherical coordinates, in the spherical notation with the n, theta, and phi, is exactly the same as it was in the Cartesian representation with an x, y, z. Okay? So that's just a very nice thing, and it's a property about rotations, and we've carefully worked out the details here to make sure that you can understand how that works. I know that this is a technical thing and it's sometimes hard to see, so I do encourage you, if you're having trouble with that, bring it up in our live session and we'll talk about it more carefully. Make sure that you have no loose ends and that you don't have any trouble with understanding how that works. All right, I'm summarizing now for you the angular momentum algebra that you should remember. You should have derived this. I'm writing it down in two forms. The most common form when the raising operator acts is the second line, not the first line, but both forms are valid lines to use. And this is an algebra that you should have worked out already. Probably you did this in the first semester of the class. If you have not done this, again, please let me know because I can review this for you. But this is a very standard thing that appears in all quantum mechanics textbooks, and it's something that you should be familiar with working on. You can get this just from the algebra of the angular momentum operators, the L plus, the L minus, and the LZ. Okay. Now, you can actually derive the result for L squared using the results for above by writing L squared as 1/2 L plus L minus L minus L plus LZ LZ. And then if you plug in with the algebra above, you see you'll get a term that has L minus L plus. So you'll have first a term that involves the L minus operator and then the L plus, but it'll be the L plus acting on the term with an M minus 1. And that's the first term that's expressed there. The second one involves the L minus and L plus. The LZ squared is easy. That's just H bar squared M squared. And when you go ahead and then simplify this result, so if you go in and you look at this, you see you have a square in the first two terms. You have a square of an L minus M, so that just gives you an L minus M. And you have a square of the L plus M plus 1, so that just gives you an L plus M plus 1. And similarly with the second term in the square root, you have two perfect squares. And when you add those together, so you just multiply them out and add them together, you find they give you L times L plus 1. Okay, again, it's an exercise that I'm sure you've seen before, but if you haven't, please take the time to do it. And again, if this is something that you are struggling with, please let me know. I do have a video that describes how you go through this from the undergraduate quantum mechanics class that I teach, and I can give you the link to that video so you can take a look at that if you would like to. And I can also talk about it with you in the live sessions. Okay, so now we can put these results together to verify that a state, so this is a coordinate state that's pointing in the theta phi direction, is given by e to the minus I phi LZ over H bar times e to the minus I theta Ly over H bar. So what that says is I'm first going to rotate about the y-axis. That's going to give me a rotation in the xz plane by an angle theta. So I start at the North Pole, rotate down by an angle theta, and then I rotate about the z-axis by an angle phi. And that's the standard way that we construct the spherical coordinates of theta and phi for an arbitrary direction in spherical coordinates. So, and remember, theta equals 0, phi equals 0 is the North Pole state. That's a state pointing along the z-axis or pointing towards the North Pole. We're also going to verify that e to the I theta hat is given by e to the I theta times this state, and e to the I phi hat is given by e to the I phi times that state. Notice that we can't actually define an operator theta hat or phi hat. You might have been told in a class and even been told that there's an uncertainty relationship between a theta hat and a phi hat, but actually that's just completely wrong. There are technical mathematical reasons why you cannot define an angle operator in quantum mechanics. But the exponential operator can be defined. And how do I see that? Well, remember, exponential, e to the I theta, that's just cosine theta plus I sine theta. But I can express cosine theta and sine theta in terms of my Cartesian coordinates. In fact, e to the I theta is just the z operator plus I times the square root of the x operator squared plus the y operator squared divided by the r operator being the square root of x squared plus y squared plus z squared. And similarly, e to the I phi is x plus iy divided by the square root of x squared plus y squared. We have to define these exponential operators in this fashion because angle operators are not well defined in quantum mechanics. And again, if you have not heard of this and you'd like to learn more about why they're not well defined in quantum mechanics, let me know and I can talk to you about that in our live session. Now, because the radial operator r hat commutes with all components of the angular momentum operator. And remember here, r is not a unit vector. R is the radial operator, square root of x squared operator plus y squared operator plus z squared operator. We can establish these results by using the Hadamard relationship, and you're going to verify them on the homework. You're going to verify that these relations actually hold. All right, so I want to end by talking about exponential disentangling. It turns out that in order to get spherical harmonics, which is what we're going to talk about in the next lecture, I need to be able to evaluate e to the I theta Ly over h bar. But in general, that is not an easy thing to evaluate because, if I write it as e to the I theta over h bar L plus minus L minus over 2I, and I think about expanding that in a BCH or something like that, it doesn't work very well because commutator with a L plus with an L minus is an LZ. The commutator of LZ with an L plus and an L minus is an L plus and L minus. And you can see the series will never end. But Baker-Campbell-Hausdorff doesn't have a regular series, so we can't even work with it in cases where the series never ends. This is a situation where exponential disentangling comes to the rescue. From using exponential disentangling, we can factorize this result. And the reason why you can see it's hard to do this with BCH is when we do the factorization, we actually get terms that involve LZ in addition to the L plus and the L minus. So the exponential disentangling identity that we worked out with the spin operators can be immediately translated to the angular momentum operators because of this group theory result that relates the identities that we can derive with Pauli spin matrices into identities that hold with angular momentum operators. It tells us that e to the theta over 2h bar L plus minus L minus, you might be asking where'd the I go? The I disappeared because Ly has a 1 over 2I in its definition. That is just equal to e to the minus tan theta over 2 L minus over h bar, e to the 2 log cos theta over 2 Lz over h bar, and e to the tan theta over 2 Lz over h bar. There's a similar one with a L minus on the right and an L plus on the left. You can also derive that from the results that we got from the exponential disentangling that we worked out in lecture 1. So we're going to use this to find spherical harmonics in the next lecture. In particular, what we're going to show is the state theta phi, which we defined as e to the minus I phi Lz over h bar, e to the minus I theta Ly over h bar acting on the north pole state. We can rewrite that as e to the minus I phi Lz over h bar, and then use disentangling on the Ly term to write it as e to the tan theta over 2 L minus over h bar, e to the 2 log cos theta over 2 Lz over h bar, e to the minus tan theta over 2 L plus over h bar. The signs changed on the L plus and L minus terms because it's minus I theta Ly that we're working with. And I must admit that at this moment it doesn't look too exciting, and you're probably just sitting there nodding your head saying, yeah, okay, I can believe that this is true, even if I haven't carefully worked it out for myself. If you are in that situation, I do actually recommend that you do try to carefully verify. Just go back to lecture 1 and verify that this is indeed the right form that we're going to be using. And I'm going to show you why this is so spectacular, because if you have been frustrated and absolutely hate the derivation of spherical harmonics in terms of all of the crazy differential equations where people are doing all kinds of changes of variables, and you sit and you nod your head and you're going, yeah, I see it, but I don't really see it, and I'm going to just take it for granted that you're doing it correctly and so forth. If that is you, and that was me when I was studying quantum mechanics, you're going to really like the way we do spherical harmonics, because we're going to actually derive the spherical harmonics from this operator factorization that we've worked out on this page. And I think it's really, really cool that you can use operators in this fashion, and I'm going to be sharing that with you in the next lecture. So that has brought us to the end of lecture 7. And as I'd mentioned, lecture 8 is going to be about spherical harmonics and how we construct the spherical harmonics using operators.